Okay, let's run through another example of linear regression. This example comes from Neil Salkind's book, Statistics for People Who Think They Hate Statistics. And this looks at how we can use high school GPA as a predictor of first-year college GPA. So we do actually find in the data that high school GPA is the best predictor of college GPA, not SAT score or other standardized test scores, but that high school GPA is numerically the best predictor. Excuse me. So if what we have here are data from 10 students about their high school GPA and their first year college GPA. On the right, we have the scatter plot of the data, and each diamond represents an individual student's responses to those two questions and how those intersect. So we have high school GPA is our x-axis, our independent variable. College GPA is our y-axis, our dependent variable. So here we have our student who has a 4.0, and they had a GPA of 3.5. So that's this student right here. The student right here was the 4.0 student with a GPA of 3.5. The regression line is the line of best fit, the line that minimizes the deviations between each line and the each data point and the line. Okay, so this line gives us a way to make an estimation of GPA as well. For example, if a student has a GPA of a high school GPA of 3.0, we can make a prediction using the regression line for what their college GPA is going to be. It may not be exactly right, but it is the best prediction that we can make based on that regression line. So we would run vertically up this x-axis until we got to the regression line, and then we would run horizontally across to the y-axis, and we would anticipate a GPA of about 2.8 for a student that had a high school GPA of 3.0. And so this illustrates that prediction. We can take a vertical line up from our x, as we did, and a horizontal line over to our y-axis to give us a predicted score for any high school GPA score. We can find a predicted score for college GPA. And we can do this, we did this before in the first video by using our regression equation and plugging in numbers. So we could make a prediction for salary and years of education, if you remember. Now, not every score is on this regression line, because the regression line is the one that minimizes deviations around that line, but it's not the line that includes all those all those scores. Remember that perfect one that we had where every dot was on the line? And that's not really what typically happens. So for scores that don't fall on that line, there's going to be an error in prediction. Now, let me show you kind of what happens with that error in prediction. So if we were to predict the first year college GPA for someone who had a high school GPA of 3.3. So if we drew our line from 3.3, and then we came over here and predicted their GPA, we would predict a GPA of 3.0. But in our data set, we had a student who had a high school GPA of 3.3, and their college GPA was 3.7. So the difference between this point on the regression line and this actual data point is called the error in prediction. So we can make a prediction based on our regression line. Our regression line is the best fit. There are going to be variations, errors in that prediction. So the distance between the point, our data point, and our line is called an error in prediction. And each individual data point is going to include some error in prediction. So we have error in prediction here, here, here. Now notice I'm drawing these lines straight up and down, straight to the regression line. And you might think that we should be drawing it at a diagonal, you know, like this is a shorter distance than going straight. So here for our 3, 3, and 3, 7, excuse me, this is a shorter distance than this line, right? Well, you have to do it in line with the x-axis because that's the actual distance. So it's not the shortest distance to the line, it's the actual distance to that x-axis. And this error in prediction is a direct reflection of the correlation between those two variables. So the correlation isn't going to be perfect, right? You know, if it were 1.0, right, that's everything on the line. I can perfectly predict from X what's going to happen to Y. So that was that perfect correlation, 1.0 or negative 1.0, right? But our correlation isn't going to be perfect. And that measure of correlation tells us kind of how far we are from perfect in that mean line prediction. So how do we find the best fit line? Let's run through the steps again. The first thing we're going to do is find the mean for each group. So we're going to find the mean for X and the mean for Y. We're going to measure the deviations from the mean for each variable. So we're going to take each individual score for X, subtract it from the mean of X. We're going to take each individual score for Y, subtract it from the mean for Y. Then we're going to square those deviations. So those X minus the mean of X individual scores that we calculated, we're going to square those. We're going to do that for Y as well. And we're going to sum those sum the column X minus the mean of X squared and Y minus the mean of Y squared. We're going to multiply the deviation for each case. Now this is called the cross product. So we're going to take our X minus the mean of X column and multiply it by our values for our Y minus the mean of Y. And then we're going to add that column together. Don't worry if you're kind of getting lost. I'm laying out the steps for you so you can go back and look at it later. But we're going to run through each piece of it together in this example. Then we're going to plug our results into our formula to find the slope, to find B. Then we're going to take our B value that we calculated and we're going to plug it into the formula to find our intercept value, our A. And then we're going to plug A and B into our regression equation. Okay, so that's the 7 steps that we're going to follow for running linear regression. So the first thing we're going to do is find the mean for each group. So here are our individual scores. We have each of our individual X scores, each of our individual Y scores. We're working towards calculating the mean. So we're going to sum these columns together. So the sum of this column is 31.4 and the sum of this column is 29.3. We calculate our mean for X. The sum of X divided by N, 31.4 divided by 10 is 3.14. Our mean for Y, the sum of Y over N, 29.3 divided by 10, or 2.93. The second step is to measure the deviations from the mean for each variable. All right, so here is our X column, and we've calculated our mean of X to be 3.14. So we're going to take each score in our X column and subtract it from the mean. 3.5 minus 3.14 is 0.36. 2.5 minus 3.14 is negative 0.64. So we're going to take each score for X and subtract it from the mean. Then we're going to do the same thing for Y. So the mean for Y was 2.93. So we're going to take 3.3 minus 2.93 is equal to 0.37, 2.2 minus 2.93, and so on. So we continue the process. Now remember, when we were doing standard deviation, I reminded you that you should be able to sum these columns together. So you should be able to take all of these numbers in this row, this column here, and add those together. They should equal 0 because deviations around the mean will equal 0 because the mean is the arithmetic center. And you should be able to do the same thing. That's a way to check your subtraction. Subtraction's where we all get messed up. In fact, when I was working through this example, I made a subtraction mistake and had to go back and figure out where I had made my error and fix it before I posted these slides. The third step is to square the deviations from the mean for X and sum the column. We don't need the deviations for Y for our calculation of regression. We do need it if we're going to calculate correlation, but we don't need it for regression. So I'm skipping that piece just to simplify it. So we don't need the deviations for both X and Y. We just need the deviations for X. So this column right here, that's what I just did on the previous slide. That was the calculations I did on the previous slide. So I'm just putting those there again. And now we're going to take these values and square them. So 0.36 squared is 0.13. Negative 0.64 squared is 0.41, and so on and so on and so on and so on. And then we're going to add this column together. So we square the deviations from the mean. So we went from here to here, we squared them, and then we're going to sum that column together and put that in our, we're going to hold on to that because we're going to need it for our formula later. So the sum of the square deviations around X is 3.19. The fourth step is to multiply the deviation scores for each case and sum the column. So we have our X column and our Y column. So here's our deviation scores that we did before. For X, here's our deviation scores for Y. And now we're going to take this number and multiply it by this number in each row. So 0.36 multiplied by 0.37 is 0.13. 0.64, negative 0.64 multiplied by negative 0.73 is 0.47.